I'll do this in 5 parts. I'll start by talking about studying versus solving environmental problems and talk about the disparity and the contrast, and then propose some ways of resolving that. I'll use a case study, and the case study is the seagrass conservation crisis. I'll talk about science communication, environmental report cards, and finally about societal paradigm shifts and how we may affect one for coastal zone management. To start with, then, proposals, research, and publications are used to study environmental problems. And the core of good science is the rigor that goes into it. And this rigor is done through a very active peer review system. And this commitment that scientists have to the process of peer review in proposals, in the research, and in the publication. And the dissemination of their results to the scientific community through proposals, peer review journals, books, workshops, and conferences. And then the scientific community develops new methods and tools and embraces and understands complexity, and ultimately, in this yearning for the truth, comes back to redo the cycle. So the proposal, research, publication cycle continues, and has done such for hundreds of years. Management, monitoring, and research, however, are required to solve problems. At the core of this isn't the scientific rigor. In contrast, it's the shared vision. The vision that is shared between not just scientists but also stakeholders. And the participation between the research community, the monitoring community, and the management community is key in achieving that shared vision. The researchers have to employ leadership to provide synthesis and communication. They support the scientific community through a variety of synthesis activities, and then that communication out to the broader community. Monitoring also needs leadership, and the non-government organizations and government agencies use this monitoring to communicate to the broader community. And finally, leadership and management and government through agencies and political leaders to the community, and the community then being informed makes effective actions to achieve the shared vision. That's a bit of a different model than the research proposal, writing, undertaking of collecting data and publication. So we have kind of a right brain, left brain differentiation. The studying problems, you have to be objective and dispassionate. However, to solve problems, you have to say, I care about this estuary, this bay, this lake, this river. To study, you have to embrace the complexity of the system, but to solve it, you often have to simplify. To study problems, you need to publish and get your funding via the peer review system with other scientists, but to solve problems, your publishing and funding is via stakeholders. Ultimately, you have to get it right when you study it, whether it's the second draft or the 10th draft of the paper or the thesis. However, solving problems often have windows of opportunity in which getting it done trumps getting it right. However, when we think about, how we can connect these two. Like the left and right hemisphere of the human brain, we have a corpus callosum, neurons that transmit information between both hemispheres. We can do that in studying and solving problems by maintaining credibility both with our peers and our stakeholders, by being tenacious both in getting the science right and getting the problem solving done. And we can apply creativity to both the science and to the applications of science. And finally, the element that we need is virtue, and virtue in the context of David Starr Jordan, an ichthyologist at Stanford University, is wisdom's knowing what to do next. Virtue is doing it. So we need science in Pasteur's quadrant, and that science is both increases fundamental understanding and is useful. And in this diagram created from a book called Pasteur's Quadrant by Donald Stokes, you see that use-driven research is contrasted against understanding-driven research. And when we have neither, of course, nothing really happens. But Niels Bohr is given as the paramount example of a pure basic researcher, this physicist who really began to understand the fundamentals of matter, but no direct application. Thomas Edison, in contrast, did a lot of research, but very use-driven, very practical and applied, inventing telephones and light bulbs, etc. And then Louis Pasteur, who did both basic research and had application. Pasteur's some of Pasteur's accomplishments included describing the microbiology of alcohol fermentation. So he really understood a scientific breakthrough because he debunked spontaneous generation, but it was for a very real problem. The brewing industry has benefited from his microbiology. He also discovered silkworm diseases and developed a germ theory of disease. He created anthrax and rabies vaccines, very practical and applied results. He built the Pasteur Institute, which is still in Paris, and is quoted as saying there are no such things as applied sciences, only applications of science. So he didn't distinguish between pure basic research and applied science. He integrated it in his life's work. So I'd like to turn our attention to a case study of a seagrass conservation crisis, and we can see where the science gets it right, but we're not resolving the environmental problem. So I have a group of colleagues that in the Seagrass Trajectories Working Group at the National Center for Ecological Analysis and Synthesis in Santa Barbara. We got together, global assortment of scientists got together and developed a seagrass database of trajectories, both positive, negative, and no change. We collected data starting in 1879 to 2006, got 1,100 observations. And what we found was, first, a very geographic bias in North America, Europe, and Australia. But for the seagrass area data, we're also analyzing density and cover data, which has a better geographic representation. But what we did find in this area analysis is that 58% of the cases, there was a negative or declining trajectory. 25% was increasing, 17% there was no change. So that is definitely of concern, and we can see that these changes occur everywhere in the globe. We also plotted that data over decadal time frames, and once we got to post-1930s, you can see in the 1930s there was a preponderance of increasing reports, but once we passed the 1930s and got into the modern decades, we see that the decreasing trajectories dominate. We plotted this net change in area with red bars being negative changes in area or declines, and blue bars being increases. So we do see these increases, but the increases are of a magnitude much, much smaller than the decreases. In fact, that's a broken bar, and those are very substantial in the 1980s and 1990s. Of most concern to us, however, is that the rate of change. And the rate of change is given as the positive rates of change in the open circles, and the closed circles are the negative rates of change. And what you see here is that the acceleration since about the 1970s of both positive and negative changes in seagrass area, but the preponderance of the area is being lost, and so we're seeing very rapid rates of loss. Why should we worry about this? Well, the ecological services of one soccer field of seagrass is equivalent to a year's worth of treated sewage from 780 people. It also absorbs the carbon emissions from an automobile traveling 12,000 kilometers, and it's worth in U.S. dollars about $35,000 per year in ecological services based on the Costanza et al. Assessment. So these beds are worth a lot. The net result of these losses, however, is that we're losing a soccer field every 30 minutes since 1980. That's what that 9% rate of change indicates. So we applied this loss rate to the area and ended up with this 30-minute loss every 30 minutes. But actually, we think that's an extremely conservative number, because when we look at the mapped area of seagrass used in this analysis and the global seagrass coverage, which isn't very well understood, but it's at least 10 times up to 30 times higher than the area used in these trajectories. So this is a very conservative estimate. It could be many, many football fields per 30 minutes. So let's look at what's happening in the seagrass field. Well, seagrass research has, in fact, corresponded to that decline has increased dramatically in the past few decades. We calculated the journal articles that were published by the major marine research journals in the past several decades, and we see that corals and salt marshes exceed the publication rate of mangroves and seagrasses, and we tend to publish our seagrass books and reports in fora that are really for other seagrass biologists, not for people outside the field. We also looked at the widely accessed media. We looked at the New York Times, the National Geographic, New Scientist, Nature. We had actually a dozen other public expressions of science, including the London Times and the Bombay newspaper. And here are 4 representative examples, and you see that seagrass, the black bar here, is clearly the lowest of all these coastal ecosystems. Salt marsh, mangrove, and coral reefs all had higher media reports than seagrasses. And we compare the media reports per scientific paper in those time periods. Overall, we see that seagrasses generate 4 or 5 media reports per paper. But that's to be contrast to mangroves and seagrasses that generate upwards of 140 media reports per scientific paper. So we have what we called our coastal charisma gap here. Seagrasses were not charismatic and haven't been accessed in the popular media. So this decline, this global decline that we're seeing is basically a secret to most of the world. So we have to figure out how to enhance our science communication. So instead of just focusing on journals and books to our brethren, we need to think about print and screen media, web and photos and newsletters, and a whole diversity of communication devices to get the word out that these ecosystems are endangered. So let's talk about science communication and think about ways we can better do that. What is science communication? I've defined it here as a successful dissemination of knowledge to a wide range of audiences, both scientists and non-scientists alike. Essentially, you're not doing anything if nobody knows about it. And I firmly believe that good science communication can make you a better scientist. That by having envisioning the story that you're going to tell can give you a sense of completeness. In designing a research program, this conceptual diagram that we used to study a harmful algal bloom in southeast Queensland, Alaska, it gave us insights into the kind of research gaps that we had and the kinds of colleagues that we needed to encourage to work with us to understand that system. Science communication can give you context, identifying the linkages and developing the comparisons can give you good insights into the ecosystem. So paired comparisons are often very powerful. Science communication can help clarify the ultimate message and remove vagueness or ambiguity in the thinking that goes into the publications. And finally, synthesis. Combining and comparing different data sets or approaches can often lead to insights. So this is a good thing to do, not just because we need to deal with the conservation outcomes of things like the global seagrass loss, but also to be better scientists. So to synthesize information for less technical audiences, these are the 3 elements that we've been working on developing tools for. The synthesis tools, and that's to provide not raw data, but interpreted or synthesized data, to provide visualizations so that people get a sense of place and they understand the who, what, where, when, and how, so that you can explain, as a scientist, the why. And finally, providing context, answering the so what question, and providing the linkages to what people care about and already understand. 2 ways of doing this, I call it the Zen of science communication, is to be enthusiastic, get excited about the science that's being involved, provide the quality time needed to make good science communication products, schedule it into the program, and provide feedback and revision so that you can improve the quality of the message. Finally, the art of science communication, and you can see from these examples of various science communication devices that our attention is immediately attracted to the moving picture, the video. That's a $1 million video. We used that video to show to some local political leaders to get us funding for a harmful algal bloom project. That video spoke volumes. There are other communication devices like conceptual diagrams. These are the thought drawings that we use to provide context and synthesis. Maps that provide geographic context and can be very information rich with many different layers. Photos to describe methods and study sites and processes and relevance. And finally, the more traditional scientific outcomes of tables and figures that can demonstrate the scientific data supporting the various conclusions. So different audiences need different content. So science writing, the kinds of things that scientists do most of the time in peer-reviewed journals, provide scientific context. They're heavily referenced. Every major statement and finding is compared to and builds on previous scientific work, and those are scrupulously referenced. The text is the dominant form of the medium. You do support it with graphics, but not as much as the text. And the focus is on the results that are determined in the scientific method and then the interpretation of those results. To contrast, science communication uses color, provides societal context, actual examples. The text and graphics are equally weighted, and the focus isn't on the results and interpretation, rather the conclusions and then the recommendations or implications of those conclusions. So there are very different styles of format for these different audiences. So the Integration and Application Network, my group at the University of Maryland Center for Environmental Science, and Loicz have had a collaboration for my tenure as part of the Scientific Steering Committee on science communication activities. And what our goal is to develop tools and provide training for effective science communication. So we produced a science communication handbook published through IWA Press. We did science communication training courses at various locations. And more recently, in fact last week, we launched Ian Press to come up with some new scientific communication products. I'll talk about this in just for a second. Ian Press's goal is to produce practical, user-centered communications, foster better understanding of science, maintain accessible prices, and enable readers to pursue new opportunities in research, education, and environmental problem solving. So these two books, Shifting Sands and Oceanography, were released last week, and then in a couple months we're producing a book called Integrating and Applying Science, a practical handbook for effective coastal ecosystem assessment. We have sections on engaging the community, where we'll talk about environmental campaigns and leadership, communication products and strategies, building community knowledge, when we'll talk about environmental indicators and report cards and ecological forecast, a section on analyzing environmental data, including statistics, models, and spatial analysis, and then a section on obtaining environmental data, including design, in situ, and remote sensing measurements.